Okay, we're mostly here. Um, yeah, first of all, there was some attempt to switch classes with the OR class that you just came from, and I wasn't able to work the logistics out for that. So, so the schedule will stay as it is. So 11 o'clock this time. Normally, this will be the quote lab time, but today we're switching it because the lab will be at 1 o'clock. Why? Because I need to tell you about event graphs. You've been hearing me mention them for some time. So today we're finally going to actually start on it. And so we've actually moved to the second topic in the lessons, which is about event graph. We're going to spend a lot of time on this. One of the reasons that I've been using this methodology for quite some time. There are other approaches. And let's see, did somebody? No. There are other approaches, and this is what I found to be the most useful and the best bang for buck. What do I mean by that? What I mean is it is actually very, very simple. There's really only one type of block, as it were, and one type of connecting edge. Well, there are actually two types of connecting edges. There are a few more complications about it, but it is very simple and yet very, very powerful. And just my experience is that it is very useful from very small models, as we'll see, medium-sized models. It's been used for, between 40 and 50 master's thesis as a methodology of building a model. And I've used it for very large models. I don't know if have they talked about a model called Combat 21? They have, no. Well, Combat 21 uses this way under the hood. In fact, it actually uses SimKit as its simulation engine. There are a number of DoD models that have used that. There are a number of models that I've been developing for NAVSUP over the past few years, which are the models themselves aren't that large, but the amount of data that they have to run is, and some of the bigger models that they run actually take a couple of days. So just anyway, and it all uses what you're about to learn here. So I'll give some examples, and then and the other is a little bit of a meta thing that has to do with how to create complex models. And this is we're going to apply it to these event graph approach that we'll have here, but it's more general than that, and it's an approach which is to start with very simple models and then gradually examine them with respect to the assumptions, and then add additional assumptions as necessary. So, and we'll see a little example of that. In particular, hopefully I'll be able to get to it, is that first I'm going to reformulate what we've done in our two models. We've had the arrival process and the multiple server queue. I'm going to reformulate those as event graphs, and then look at examining some of those assumptions. So one thing I think was mentioned yesterday, that in the basic multiple server queue model, there is no capacity. The queue can be as big as you want. But what if that's not the case? And think of the In-N-Out burger on Del Monte, for example, or maybe like a waiting room somewhere, or anywhere there's just a finite amount of things available. The basic model that we have won't do that, but if that is an important thing, and sometimes it is, then we'll have to look at that. All right, so this is like 90% of everything that you need to know about event graphs. And and that's why I like it, because it's very, very simple. What we've seen is that a discrete event model consists of 4 pieces. There's the parameters, the state variables, the events, which are the state transitions, and then the scheduling relationship between events. So what event graphs do is they take that last 2 pieces, the event and the scheduling relationship, and they turn it into a directed graph. And so in event graphs, we have a node, the nodes, which are the circles, and those represent the state transition piece. The edge, or the arc, represents the scheduling relationship. So, and this is the canonical form, if you will. And here's how it works, is event A, this is event A, and that stands for its state transition, and this is event B, and that stands for its state transition. What this little piece means is that at some point, event A occurs. What does that mean? An event occurs when the event list decides that it happens. So the event list, as we've seen, events kind of get put on the event list and then they come off as their time arrives. You know, just like a calendar, you know, in a way, your calendar is kind of an example of this. When you schedule an appointment or a meeting or even a class, you kind of put it on the calendar, and then it's not going to happen right away. It's going to happen whenever it happens on the calendar. Exactly the same in the event list. We're scheduling these sort of events. You can think of it as a meeting sometime in the future. And then the event list is what kind of marches time along. The difference is that in real time kind of, at least in a non-relativistic sense, you know, moves at a constant rate, whereas in a discrete event model, time moves in jerks and starts at different leaps. So when event A occurs, that is when the event list decides that A has occurred, then it processes the event. So now what does processing mean? This tells the designer, at least, or that the modeler has decided this is how this particular event, what this is going to do. First, it executes the state transitions inside, which are defined by the user, by the modeler. And then this is a Boolean condition. This is either true or false. This is typically some function of the state. Well, it is some function of the state variables. So if it could be either true or false, then that means that is, and as we'll see examples, it'll either be true or false depending on what the state of the simulation is. Is it clear that this condition, it doesn't make any sense for this to only depend on parameters? Does that make sense? Remember what parameters are. Parameters are values that don't change. So if this depends on a parameter, it's always going to be true or it's always going to be false. And so there's really no, and if it's always going to be false, then there's no point in even having it here. Now sometimes parameters can be involved in it, but there will always be a state variable that's involved. So it says if this condition is true, then it's going to execute this scheduling edge. And what does it mean to execute the scheduling edge? That means that event B, which is at the head of this edge, event B gets scheduled after a delay of t, which is part of the properties of this scheduling edge. So the scheduling edge has 2 properties. One is the Boolean condition, which is either true or false at that particular time, and the delay. And that's it, basically. And the amazing thing is, using nothing more than this, you can actually build just about anything. In fact, now the guy who came up with this is his name is Lee Shrubin. He was actually one of my professors in graduate school, which is where I learned about this. And a number of his students have developed various properties of this. One of the things that one of his students had a very interesting result, which is that this in itself is what's called Turing complete, which means that anything that you can compute or build using computer, you can do using this approach. Not that you, I mean, basically you can build an operating system using this. It wouldn't be ideal because under the hood, in order to execute this, you need an event list and stuff, but okay. Yes.
And the Boolean condition reference for delay. Can you second Boolean condition if delay is less than or greater than a certain value?
Yes, absolutely, yeah. Yeah, and that's maybe one exception to the quote parameter thing, because the delays are often considered parameters. But yes, that is possible. Although, yeah. Okay, so these are the steps to create an event graph model, and then they're very simple. But as you'll see, it's just like, well, you are, well, we're English speaker here, at least most of us, or whatever your language is. You all have a certain, you all have a language. You know all of the words that are in the most brilliant scientific papers or the most amazing literature. You know what those words are. You have all the words are in the dictionary. You're going to need to use those words when you write your thesis or paper or whatever it is you're doing. So knowing the words is necessary but not sufficient. There's a bit of work that you have to do to create a brilliant paper, a brilliant thesis, an amazing piece of literature. So the words are the same, but there's some extra stuff you got to put in order to turn it into something. And the same is true here. In other words, this is the entire process for creating one of these discrete event simulation models. That's all you need to know. The devil is in the details, though. So just like you know all of the words, but turning them into something brilliant takes a little bit of extra sauce. So define parameters. And this is, in my experience, and as they say in the internet, your mileage may vary, but this is my recommended way to build all the models that I'm going to make you build. So the next written assignment that you're going to get is going to be, and the ones you're going to get are going to be word problems that say, here's a situation, and then you need to create one of these event graphs. And that's what's going to be. Now, in addition to that, I'm going to ask you to be writing computer programs that implement some of these, but that's going to be the easy part. So defining parameters, always start with this. Why? Because the parameters, and it's particularly simple in this class. It's not so simple when you're kind of out in the wild, but the parameters are almost always going to be pretty much a very small step from the problem description. Now, defining state variables, that requires a little bit of thought. And the full definition of a state variable includes its initial value. So when we defined the number in the queue as a state variable, we also had to say, well, we're going to start with none in the queue to begin with, or the number of available servers was a state variable, but it was not fully defined until we said, okay, initially all of the servers are available. In other words, S is equal to K, as said. And then once you've done that, once you've kind of taken an effort to do this, then identify what the state transitions are. So, and it should be sort of obvious that you can't define a state transition until you define a state. Those are the events. And then finally, the last piece is to define the scheduling relationships and then write those as edges. So, okay, so I'm going to, these examples are in the slides, but I want to do this a little bit more live for you just to kind of show. So here's our arrival process. So we first define our parameters, and our parameters are going to be this list of inter-arrival times. Our state variable, okay, we called it n, and the number of arrivals, initial value 0, and then the state transition. So initially, we had initially n is 0, and then upon an arrival, we had n goes up by 1. Again, simplest possible non-trivial state event graph. Okay, so what I want to do, sure, just, right now. Okay, so now there's on Max, there's unfortunately this is a commercial program, but this is one that has worked very well for me. All right, so we defined our state variables and our parameters just for completion. Let me define our T sub A is inter-arrival times, and then n is the number of arrivals, and that's initially 0. It's kind of small. Let's see if we can we make that bigger. All right. So now that we've okay, so what we want to do is we want to first, you can always start with a run event because, and what's nice about the run event is that all we need to do is initialize our state variables. And so if we've defined our state variables, okay, then including initial values, then all we have to do is kind of write that. What's the big benefit of that? My experience is that has overcome sort of a blank page syndrome. Whether writing a paper or a document or doing one of these things, in the beginning, you're staring at a blank page, either physically on paper or a blank document. And there's sort of I don't know, maybe you don't experience this, but I do. When I'm staring at a blank page, it's like there's a lot of hesitation to even get started. But once you get started, then things kind of start to flow. So this is a way of always getting started. So that's why it's important to spend your time defining your state variables. And once you define them, you can always write down an event. This event is always going to be there, even if you can't figure out what to do next. But the next piece was the state transition was we have another arrival goes up by 1, and that was we were calling arrival. And so that's an arrival event. And what we do is underneath, we put the state transition. The exception to this is that now, as these events get bigger, and sometimes the state transitions get a little more complicated, and in those cases, it's convenient sometimes to kind of say, okay, here's the event, and then somewhere else I'm going to put the state transition just to keep the graph itself fairly clear. But for small things, you can actually kind of see what's going on there, and the question you then ask yourself, notice that I'm not trying to connect them yet. I'm first trying to define all of my events. And once I've defined all of my events, then I can start deciding whether or not I can connect them. So the criterion is, are these all of the state transitions I can think of for all of my state variables? So is there anything else that can happen to my state variables? And in this case, I can't think of any, because they show up and we're going to get one more. So when I'm done, then I can start drawing things. So run is going to schedule, you say, well, run is going to schedule the first arrival event with a delay of well, we were calling it T sub A. And just to, let's make that a subscript. Okay. So this says run will schedule arrival with a delay of T sub A. And is that all that run, is that the only thing that run does? In this case, yes, we're done. Now let's look at the next event. Okay, what does the arrival event do? Well, it increments n by 1. We've already done that. And what does it schedule? Well, it schedules another arrival. So how do we represent that? We represent that by saying it schedules itself. And is there a delay? Yes. So the delay is another inter-arrival time. So now one thing to, should have done this. Okay, just a little bit of terminology. Notice that when we defined this, and let's make that a subscript 2. When we defined our inter-arrival times, I put them in curly braces. Normally that denotes like a set, in this case, a sequence. Whereas in the event graph itself, they're just a single value. And what that means is get the next, if this refers to a sequence, then just get the next one. In practice, when we implement these are going to be randomly generated. Okay, and we're done now. This is that's the thing. Okay. So, and I kind of do all that in here. And so here's the final thing. And okay, I got it right. That's always good to know. As we saw yesterday, when it comes to doing arithmetic, I'm a little challenged in that area at times, but that's what calculators are for. And I remember a teacher saying that, no, you're never going to always have a calculator available. Well, guess what? Take that, Mrs. Gallagher. Okay, so any questions about that? Okay, very straightforward. Now, let's do the same thing for our multiple server queue. So we have our inter-arrival times of customers, we have our service times, and the number of servers. So those are the parameters. We had 3 state variables. Q, the number in Q, it's initially 0. The number of available servers, initially K, the total number of servers, and the number in the system, which is initially 0. And I think, well, okay, there's, bless you. Okay, so let's, and actually what I want to do is I want to do, instead of this, because this is a derived value, I'm going to do another one where I'm going to define, I'll call it N, and this is going to be the number served. And that's going to be initially 0. So instead of the number in the system, I can always get the number in the system if I know Q and S, but I don't know how many I've served. So I'm going to add that as a state variable. Just for okay, so let's go back to here and pretty much do the same thing. So we have, I'm not going to rewrite the parameters here, but okay, we have our run event, and for that we can initialize Q, initialize S, and then I'm going to add this N, which are the numbers served. I'm not going to add L. I'm not going to add the number because that's a redundant one. Okay, so now, So here's the thing that here's an approach that I found to be useful. Pick a state variable, in this case Q, and what is it that could cause Q to change? Well, one thing that can cause Q to change is it will increase by 1 if an arrival happens. So we can call this arrival to system, or we can call this anything we want. Just don't call it late for dinner. But Q goes up by 1. Q. And if you like the, plus equal, or, I discourage the plus plus, but if you're insistent on that, I won't totally object, but I'll be annoyed. That's all. Okay, what else could cause Q to change? Well, when a customer goes from the queue into service, and so the queue gets decreased by 1, we were calling that event start service. Again, you don't have to call it anything in particular. So, but when that happens, Q gets decreased by 1. Okay, so now is there anything else that can happen to the Q in this model? I can't think of any, but I may be missing something. All right, but I think I'm done. So let's move on to another state variable, S, the number of available servers. So what could cause the number of available servers to change value? Well, we could lose one, lose an available server when they start serving a customer. And we already have an event for that. It's called start service. So we can add that state transition. And is there anything else? Well, if we're always losing servers, then at some point we're going to kind of run out. But when they finish serving a customer, then we have another server available. And so no event is covering that. So that one we were calling end service. And the state transition for it was S plus 1. Okay, so now is there anything else that I can think of that can happen to the number of available servers? Not that I can think of, but that doesn't mean there isn't one. And I say that because when you're doing a model, I'm encouraging you to go through the same thought process. Pick a state variable, try to think of all the different state transitions until you run out. You can't think of any more. But what sometimes happens is as you go along, all of a sudden, I forgot one. And when that happens, then usually what you need to do is either it might be attached to an event you already have, as we had here. So the start service event decremented the Q, but it also decremented S, as it turned out. So we had an event that we could already reuse. Or if you don't have one, then write a new event. So every state transition must occur in one of these events. Okay, so finally, our last one was this state variable I added, which are the numbers served. And okay, so the number served, when somebody arrives, that doesn't change it. When somebody starts service, that doesn't change it. But when they finish service, now somebody's been served. And we have an event that we can just add that to. Okay, and remember, this N is not the same as the N in the arrival process. It's a totally different N. Okay, so now I've gone through all of my state variables, all of the state transitions I can think of. And so I believe these are all the events that I have. Now, I might be wrong, but as far as I'm concerned, I'm ready to at least start the scheduling. So how does that look? What does that look like? Well, okay, just as with the arrival process, run schedules an arrival, and arrival schedules another arrival. And here I'm going to see. I'm going to cheat a little bit. I'm going to copy this guy. Oops, no. What I wanted to do is copy this guy. Just because, okay, so I've already. All right, so that is the, let's make this a little nicer. Okay, so that's the arrival piece there. And then, okay, what else? Now, an event can schedule 0, 1, 2, 3, or as many other events as necessary. In our arrival process, it only scheduled one, but in this one, it may schedule a start service. And I say may, that the Boolean condition, and I like this little squiggly thing, you know why? Because that's what the guy who invented them did. And what's the condition for this? The condition is that there is an available server. And now notice that I've said there is an available server, but I can express that in terms of the model. So I can't, English doesn't work on the model. The model only understands things that are expressed in terms of parameters and state variables. So in this particular case, S bigger than 0 means there is an available server. Now, one thing, notice that I'm not going to put a delay on here. So why is that? Because of the default. I could put a 0 there, but the default delay on a scheduling edge is 0. So if I don't put 1, it's 0. Just like in instance variables, the default value is 0, in Java at least. And so for scheduling edges, the default value is the default delay is 0. The other thing that I probably also should have mentioned, notice that in the arrival process, we didn't have a Boolean condition. And this is the opposite of programming languages. The default Boolean condition on a scheduling edge is true. So if there's no Boolean condition, it's always executed. If there's a Boolean condition, it's executed only if it's true. And as we saw when we did it by hand yesterday, if you remember, that second arrival showed up, there was no available server, so it did not schedule. Okay, now the start service, when we start service, we schedule an end service sometime later after a delay that we're calling T sub S. And let me make this I don't know why. Okay, so we put the delay there. And that's unconditional because we always, once we start, we're always going to finish. And that's an assumption we need to look at some point. But when we finish service, when a server finishes, then they may finish. They may choose to execute to start service on the next person, but only if Q is bigger than 0, and that's how we express it here. So when we finish, when a server finishes, if there's somebody in the queue, then we will start service on them. If not, then we don't do anything. And so the English words, there's somebody in the queue, is represented in the model by the expression Q bigger than 0. So everything that we say about our model, we need to express in terms of the model. And this is it. This is our full model. And hopefully I got it right. Okay, so here state transitions, and in the slides I sort of re-walk you through, but I wanted you to see it live just to, and then okay, so here's the final thing. And oh, okay. So now actually in the slides, notice that I did a slightly different model. I did the one where I explicitly put L in, the thing that I said was not a good idea. So, but in this particular case, it's okay. Why? Because it's such a small model. In a bigger model, and I speak from experience. In fact, just a couple months ago, there was a large model. For some reason, actually the client, the sponsor, wanted an explicit variable for this. I said that's not the great idea, but they were the, it's the golden rule. The golden rule. He who has the gold makes the rule. So Anyway, so I put it in, and of course it got out of sync. So it, but and I fixed it. But okay. So here's our final model, except in the one that I showed you, this was the case. This was not here, and then it did this. So that's just what's the difference between what's in the slides and what I was showing you live. This is. Okay, so any questions so far? This is all, I mean, this seems really, you know, simple, and when I was sitting where you were and kind of learning all this, it was, oh, yeah, got it, no problem. And then I got my first formulation problem, and it was like, oh, okay. So it seems really simple. It seems very straightforward. Why? Because as the instructor, I have the luxury of being able to kind of pick examples that I've already done, and I get to torture you with examples that you haven't done.
Sure, I have a question. So when I assume you get complicated problems, so we just follow the same algorithm, figure it out, that we just something we just had it.
Yes, absolutely. Yeah. For those remote, the question was, since I said, well, if you forget something and need to add it back in, do you just sort of add the event and add a scheduling edge or whatever? And the answer is absolutely yes. I mean, it's in practice, it's an iterative process. In other words, it is a rare thing to be able to kind of come up with the final model, full blown, works perfectly the first time. That's just like kind of writing a complicated program and having it run correctly the first time. Just like that, you can, you know, fits and starts. But the difference is that the language is just really very simple. The language is state transition event, schedule. That's it. So now so here's the thing is that now that we've done a very simple model, what you should always do in a situation is say, okay, start with the simplest model that does something about what you want. So if we're modeling a queuing like situation, the multiple server queue is a natural place to start. But let's look at what some of the implicit assumptions were. In fact, here's one that we're not going to deal with immediately, but we will eventually. The assumption of an arrival using an arrival process, or have you heard the term Poisson process by any chance? Okay. There's an implicit assumption about a Poisson process. I mean, you can think of an arrival process like a Poisson process, but with different inter-arrival times. Implicitly, that is actually assuming there's something called an infinite calling population, meaning that the arrival rate is constant no matter how many are in the system. Many times that's a reasonable assumption. So for example, if I'm modeling, like say the Safeway on Fremont, for example, there are a little, maybe 120, 130,000 people on the peninsula. And maybe if there are 50 people in Safeway, then has that appreciably altered the rate at which potential customers are coming in? And the argument is it probably doesn't. If you have that many, then have it, 50 out of 120,000 it isn't going to decrease it by very much. If I'm in a town of 100 and 50 people in town are in that store, that's a very different story, right? In other words, so this is one of the implicit assumptions that we were making. Another we were making, and this is what we're going to kind of look at, is that there was an infinite amount of waiting room. Oops. So what if there isn't? So what happens if somebody shows up and there's no room at the end? we assume that all arriving customers join the system, but, and once they join, they finish service. But what if that's not the case? So what we want to do is we want to observe our system and match the assumptions, or at least kind of start adding assumptions. So for example, so the first one to look at is there's only a finite amount of waiting room. And so we look at our system and say, what happens? So you come up, you have a hankering for a burger, and you're driving down Del Monte, you come to In-N-Out Burger, and the line is all the way out to the street. So now, some people actually kind of block Del Monte by joining, but okay, but you really want that burger and you don't even want to wait on that line. So, and you know that there's a Burger King, there's a McDonald's just sort of a little down here. And, you know, as much as I like In-N-Out, if I have a hankering for a burger, I'm going to take the nearest one. So what I'm going to do, I'm going to drive on. So let's look at that assumption. So in other words, this is actually a phenomenon called balking. It's not, the runners don't get advanced. That's a different kind of balking. This is where you instead, you know, a potential customer comes to join the system. They see it's full, they go away, you lose them. That's it. So let's model that. And I want to do it live, and I'm going to do it a little bit more quickly. So what I'm going to do, well, oops. All right. So what do we have? Well, we have the basically here. It's back here. All right. All right. So what we're going to do is to our multiple server queue, we're going to add a parameter. I'm going to call it C, which is the capacity of the waiting room. So in addition to our state variables that we had before, now I'm going to have, okay, I'm overusing this word N, but okay, the N is now going to be the number of potential customers, kind of like we had before. And now I need another one because what am I interested in? I might be interested in how many what percentage of potential customers am I losing because of this finite capacity? And so my potential lost customers is just going to be the number that I've lost over the total number that I could have had. Okay, in addition to our usual suspects, as it were, meaning the oops, not this. Go. There you go. All right. So our run model is going to define, just as before, we have Q, we have S, same as before, but now we have what I'm calling, now my N is the number of potential customers, and this is the number who balk. And so now I can't, so now let's start with this, well, let's start with N, the number of potential customers. So just kind of informed by the arrival, we can have an arrival, but now that just increases the number of potential customers. So this is a potential customer, and that's actually all I need for that. But now let's look at our state variable Q. So now I need another event that says, because they're not all going to join the queue. So I'm going to call that join queue. And that's going to increment my state variable Q. And then what else can do, what else can change it? Well, I have a start service. And that will decrease Q. Okay, and that's it for queue. But now let's look at this bulk thing. So do any of these events correspond with somebody leaving the system and not joining the queue? No. So I need another event. What am I going to call it? I'm going to call it bulk. And what does bulk do? Bulk will increase by 1 the number of bulk customers. So if this event occurs, that means that somebody has left the system. And I now have, or I mean, they've potentially joined, but they have decided not to. Let's move you over. And then finally, looking at S. We have, we can get one, or we can lose one, and we lose one here. So this is the same as before. Okay, so these are all the state transitions for this model. So do you see how we had to kind of alter? So we couldn't just kind of reuse, we couldn't just reuse this, because this arrival incremented queue. And we can't do that because just because somebody shows up doesn't mean they get to join the queue. And now, okay, so I'm in the interest of time, I'm just going to draw these first. So now, okay, so here's the, oops, no. These are the same as before. All right, but now I need to look at what happens at the arrival event. So 2 things can happen. I can either join the queue, and I will join the queue only if, under what condition? That there's room, yeah. And so how can I express that in terms of my event graph? If Q is less than capacity, then I can join. But what is the situation that I don't join, that I bulk? That is the condition that Q is equal to the capacity. In other words, if the number in the queue is exactly equal to how much room I have, then I'm not going to join, I'm going to bulk. And then these are all exactly the same as before. So when I join the queue, I don't necessarily even get service. And when I finish service, I don't necessarily schedule a start service. And then my delays are kind of the same as before. It won't. So I have my inter-arrival times and my service times. Okay. So here's the same, here's the multiple server queue model, but with finite capacity. What is the difference? The difference is that here, not everybody gets to join. And I will only join the queue if there's room, and I will bulk otherwise. So at the end of this, when I run this model, I will have state variables B, the number of bulks, and N, in this case, the total number of potential customers. And so I would be able to compute B over N as the percentage of lost customers. So in this particular case, if I'm saying, well, what would be the impact if I added, say, one more slot to my capacity? I could then run the same model with that different value of capacity and compare the results. If the new measure made it worthwhile, then that's a good idea. If the new measure didn't make it worthwhile, then it's not a good idea. But what's the point? None of the properties of any of these models is a law of nature. This is something which comes from the definition of the problem itself. Okay, and there's one more model that's in the slides, but I didn't get to that, but that's okay. Now, any questions from the room or from online? If not, then now the next part is we're going to start putting this on the computer. And for those of you using Java, there's the computer assignment should have been posted. I don't know if you've seen it, or if you haven't, make sure that you check that out. And if you're doing Java, use the Java one. If you're doing Python, use the Python one. So we will reconvene at 1 o'clock on the other, for those of you remote, it'll be on the other Zoom. And I'll basically sort of troubleshoot and answer any questions that kind of come up about that. So anything else? And if not, then have a good lunch.